Find the answers to questions you may or may not have asked yourself here at Kaleidoscience, Conversations on Cognitive Science. This episode is hosted by Sönke Löw and Sophie Kühne.
We've all heard of AI. AI is a common topic in the media, and we've all heard of psychiatric conditions. But how can AI be applied to a psychiatric condition? And why would we do that? Today we're here to talk to Nadja Ging-Je, who is a postdoc at Brown University and an expert on computational psychiatry, cognitive neuroscience, and mathematical psychology. Welcome.
Thank you so much, Sophie. Nice. Thank you for having me.
And as usual, we like to play our welcome game. And for that, I will read the beginning of 5 sentences. And I want you to spontaneously continue each of these sentences. And the first sentence would be, as a kid, I always wanted to be.
A soccer player.
Okay,
that's very
nice.
fun.
The second sentence is, if I was an emoji, I would be.
Happy.
Nice.
Like the smiley one?
The smiley one, yeah. With the stars, with the stars as eyes.
Cool.
I think that's a new one. I think we never heard that before.
It's also my favorite one to choose from.
Nice.
The third sentence is, my favorite thing to do on a day off is...
Hiking, sports, like just moving. I like diversity. It's not something that I can say I want to do just always this particular thing. I like to, go and hike in the mountains and then go sailing and then do rollerblading, like just no repetition if possible.
That's very fun.
Right now, I'm most fascinated by...
Good question. I'm most fascinated by the speed with which we have to keep up with. Just changes in general. I think it's very taxing on the human capacity to be exposed to this speed of change and speed of uncertainty or change in different sources of uncertainty. I'm very fascinated how we can keep up with that.
Okay, and the final sentence is, I know it's time to call it a day when...
I get moody.
That's a good indication. Sophie already mentioned that you are currently at Brown University, but can you maybe quickly walk us through your own scientific journey, so how you got to the position you are at right now?
Mm-hmm. Yes, of course. So I am originally from Switzerland, where I studied economics. I come from industry, and I went first to applied university, and I was interested in behavioral economics and economic theory to explain group behavior, but also individual behavior, like within organizations. But then I got very fascinated by the brain, and I wanted to go to the US. So I only applied for PhD programs in the US because back then I loved this flavor of meritocracy. I loved the flavor of choosing your own program, not being limited to be in a specific department. And that was just so fascinating to me, how I could bridge the different fields. And so I applied to a PhD program at The Ohio State University, where I was able to work with an advisor in psychiatry, an advisor in neuroscience, and an advisor in psychology. So that's how I was able to already from day one on actually bridge my expertise across different disciplines. And it was because of a fellowship from the Swiss NSF that granted me the liberty or freedom to, from a very early on, determine my own research program or the questions that I wanted to pursue. And so I was very interested in computational psychiatry applied to the context of ADHD and autism. And so I did that during my PhD, and then it was actually a little bit of a coincidence how I landed a postdoc. I wasn't really planning on it. I wanted to skip postdoc and look for a faculty position because I have been in industry also leading teams I felt equipped with the leadership skills and with the experience to actually already kind of like go ahead with it. And then there were multiple stars that suddenly started to line up. And so there was this opportunity coming up to join Michael Frank's lab. And Michael Frank is I call him one of the founders of computational psychiatry. He has a very strong breadth and depth of a research program that he is selber pursuing, which I find it's incredibly remarkable, and it's also fascinating. And so I was like, okay, no, I have to learn from this person before I go and start my own lab. And this is how I joined Brown. It was a informal meeting that we had, and just like the connection in research interests on multiple ends, where I said, okay, I would love to study the brain a bit more, still in the application of computational psychiatry, but also stronger with like theory of models at the different analytical levels. I had been trained under Roger Ratcliff for the diffusion decision model or sequential sampling models, which is very powerful computational model to actually understand behavior, in particular how people make choices and why they how fast they make choices, why they are sometimes slower with these choices and sometimes faster. But I wanted to understand also what happens within the brain, like what are at the circuit level the interaction parts that make sometimes people more distracted and other times less distracted, why we sometimes lose our train of thought, why we are sometimes feeling indecisive, but at the same time also very impulsive. So there are all these like contradictions at the behavioral level that I felt I need to understand why the brain is doing what it's doing. So, and that's why I started my postdoc here. And I was fortunate that I, during my postdoc, was able to secure grant money to now actually create a digital tool. And I have a strong vision to do this, to create this digital tool and form it into an adaptive agent that helps us with reassessing when we are jumping to conclusion, when we might have to rethink our belief in interactions with others, but also our belief about our own skills. I do think one of the main key take-home messages or experiences that I was able to acquire when I was working in the clinical setting during my PhD is that you have this very snapshot-like discrete interactions with patients. So a psychiatrist or a clinician is not constantly following your steps. And very often that it's challenging to help someone if you aren't able to go with them and dive into the situation where a problem occurs, or when a kid comes and says, I have no friends, or I'm bullied all the time. It's very hard to actually figure out why this is the case. And especially with these mental health conditions like ADHD or like depression, they are very complex. It's not that we have like one mechanism that can explain why someone has ADHD or why someone has depression. There are risk factors that we have learned about, genetic, family risk factors, but we also know that there are protective mechanisms. So depending on the structure, how you grow up, what your friendship looks like, your family support looks like, you might be able to compensate for many, many different symptoms for a long time. And so my idea, and where I have great hope in AI, is that it's actually almost like a personal device that is a bridge between what you don't know about yourself and what someone as like a therapist can mirror you. And so that's kind of like the idea. And I have been developing a game to dissect mechanisms of rigidity, because one of the aspects that we have seen is very commonly associated with almost all mental health conditions, no matter what, is that we are stuck. We are stuck in a routine, we are stuck in a specific mindset, or we are stuck in a specific behavior. And so that is something that is very commonly seen across these conditions, but we don't know the mechanisms. And it's very important to understand the mechanism, because these different stickiness might need different treatments. And so the idea is that you are dissecting these mechanisms with models in a playful, gamified environment that is engineered with the computational models that probes you, and then learns from your patterns and gives feedback to you directly. And I feel it's not that different if you wanna at a very, very high level. I don't want to equate that it's the same problem, but just think about like Roger Federer or another tennis professional. They have coaches and camera everywhere that looks at them, how they play. The coach can exactly say, in that moment you would actually get more speed on your ball if you would have the left foot a little bit more forward, or if you tried this, or if you tried that. And so this is how I see an AI agent actually be able to kind of like get the best out of your potential, saying like, oh, maybe you could study it this and that way. Maybe you could use this learning strategy, or maybe when you're distracted, why don't you go first for a walk before you go and do the heavy math exercise, or maybe the other way around. So there are these like possibilities that I think we haven't touched at all, and which I think AI is actually opening up almost a completely new field or potential for us.
Okay, I think that's all really cool, but I feel like we need to answer some a little more basic questions for you. So you already talked about computational models in psychiatry. Could you explain a little more what computational models are, like a little more simplified?
Yes, so computational models are, you could say, like mathematical blueprints. They aren't what often people think is what computational models are like mobile that would explain exactly the real world, but this is not the case. It's more like when you think about looking at a globus or looking like at the planet, right? So there are some aspects that are very detailed, so you can see like the shape of each continent, but you can't necessarily see the mountains of Switzerland. You don't see that there are Alps that are much, much higher than anything you can actually find at the East Coast in the US, right? And so there are some abstraction that you kind of like abstract from, and then you only keep the most important things. And these computational models, what they do is they try to mathematically explain how we make decisions, and it reverse engineer, or it uses, for doing that, it uses as an input what we respond and how fast we respond. And then it goes back in time and says, okay, if I know that this is how the behavior looks like, what are these different interaction parts during these decisions that explain the behavior that I can actually observe? So it's kind of like going back in time and trying to simulate these unobservable factors. Because when you think, very often when we go to a store and we are having to choose between 5 different, let's say, Kellogg's, right? So we might have a very clear preference towards one Kellogg's when we have tried many of them. But if we haven't tried many of them, then we might actually stand in front of that shelf and take a moment to think. And the question is exactly what happens in the brain, or what happens in our physiology, in our eyes, with our body, what happens while we are making these decisions.
And you already talked about like the reaction outcome and the reaction time as an input, but also like your eye movement, like where you put your eyes, is that also like a measurement that goes into like what are the components that are measured that we can model?
Yes, so it's there. I think the components are infinite right now. There have been people using eye tracking to look at where you look at. So we call that also gazes. Then there are people who look at pupil, because pupil has been linked to a specific system of neurotransmitters in the brain called norepinephrine that tells you like how vigilant you are. And there are some specific hypotheses of why that could be important in shaping your behavior. And then you could also use skin conductance. So there are, for instance, people who look at how sweaty your skin is. That could be an indicator of how nervous you are or how anxious you are while you are making decision. People who look at heart rate is another measure that they have looked. Of course, the brain, EEG, or being in a scanner while making decisions, has also been used. So there are all these different aspects. I think what is important is that what is also, like, for me, important from a cognitive psychology standpoint is that we are always working with a theory. We use computational models because we don't want to only have a specific framework or concept that wouldn't make predictions. We use a computational models to make very clear predictions. If we change this, then we think this happens. And the model and the data helps us to actually assess, is this relationship the way we think it is, or is there something that is missing? And so it's like similar in physics when we are observing something empirically. Like we observed that the distance to the moon is always the same, and it's always kind of like the ebb and flow depending on in which time we are, changes in a very predictable way. We have learned about these aspects by observing. And so the underlying assumption here is as well that if you are observed and you use these measures, you can learn about physical or law-like patterns.
So if you build an AI and that is trying to choose Kellogg's, you feed it the information of the different people looking at the cereal aisle. Like, let's say you can do like an EEG, you can do like some eye tracking. You can also look at which ones they, for example, read the label or something. And then in the end, what does the model predict?
So, for instance, we know when we use eye tracking that people are more likely to choose what they look at the last, or they are more likely to choose what they look at for a longer duration. We know that when people look back and forth, that they are more indecisive. So there are these specific, we can also call them like biases, where people just use heuristics. So we also have that very often in behavioral economics, where we know that, if something painful happened to you right now, and I ask you how painful it was, you are more likely to say, oh, it has been super painful. It's a 10 out of a 10. But then when I ask you a week later, you might say, actually, you know what, it has not been that bad. So there are these heuristics that people use while they are making decisions, and some of them might guide our attention system or might guide the way we look at information. Why sometimes we observe that people do not even consider any other options. There are people who when you have a very strong preference, you might not even look left or right at the other cereals. You might just go straight ahead and pick that one cereal. And so, for instance, we know that people with autism, a certain type of autism, I would say not everyone with autism has that, but some of them have like repetitive patterns, and they are, for instance, more rigid in their choices. So they are more likely to just always choose the same color and maybe not even explore the other options. And so that is something that we could capture with the model and this eye tracking. And then we would hope that when we understand when exactly in this process attention plays a role, that we could also say, okay, now we can create an intervention. If it's just that people do not see the other options, maybe we can from the very beginning have something in the shelves that makes you go and scan first through the 3 alternative options before you are able to choose one.
Okay, and before, so let's go a little back to the models again. You already mentioned the diffusion decision model. Could you name like some common models and maybe some of their like use cases?
So the diffusion decision model is one of a larger category called sequential sampling models. And they are all based on an information theory that has been developed in the 60s that says whenever we go and we have to make a decision, we are going to, in mathematical terms, sample. We are going to sample evidence. So bit of information we are going to extract from whatever we see in our environment. And then we are going to take that all together and we call that also accumulating. We are going to take this all together and then make an informed decision of what we want to choose. And so the diffusion decision model has been developed by my previous advisor, Roger Ratcliff, in 1978. But it has been a hypothesis and the theory has been developed much, much earlier, and it's actually coming from economic theory. So that makes me, of course, very proud because I had been studying economics from the very early beginning on. And that had been developed in the 60s already. And there has been so-called wild accumulator models. There has been afterwards, when Roger had coined it all together, there has been other models that are very related to the diffusion decision model, like linear ballistic accumulator models or Ornstein-Uhlenbeck model. And all these different models just make different assumptions about how we make these decisions. And what is very important here is that they are all under the umbrella of sequential sampling models. And that's so powerful because these models have been used in neuroscience. So to account for data in monkeys, to account for behavior in rodents, to account for behavior in humans, when they are making decisions about perception. So they see, for instance, moving dots and they have to decide which one go to the left or right. But they have also been used in economics. They have been used to see how do people actually choose between a chocolate bar and a cereal? How do people choose between a car and a house? So it has been so widely applied since these early days, and it has withstood all critique and alternative explanations. And I think that's why it's so powerful tool, or such a powerful model.
I think that's really cool. I have two more questions about this. So all of these models could be applied to people choosing cornflakes, for example, in a supermarket setting. And I forgot my second question.
Yes, also definitely they could all be applied to how people make choices. Sometimes people, there is now a new emerging field where people want to extend these models and explain group behavior. I'm very eager to see how this works out. I think in economics, we are always distinguishing between microeconomics, which tries to explain behavior individually, and then macroeconomics, which tries to explain group behavior, like in finance market and in specific market settings. And we haven't been really great in the theories bridging so that they would also explain group behavior. So in economics, we had to we realized that we have to use different models to explain group behavior versus individual behavior. And I'm eager to see how this pans out in this research field. I don't think we have a clear answer yet, and we will see. I do think that when you are in a group setting, there are specific group dynamics or power dynamics that might actually play an additional factor that are absent when you are in a supermarket and you make choices, or when they are absent when we think about the psychiatry context. What we are often interested to understand is what drives people out of their bed. When do people try to go about their day, and when do they avoid? So there is some avoidance behavior that is often clinically important to understand and to overcome. And one of the ideas is that you can apply these models to study when do people avoid aversive events, like when do they try to avoid an exam, and when do they actually approach it in a good mindset proactively, these kind of things. Yeah.
And my second question was, you said these models are sequential. What does that mean?
So sequential just means that you sum up. So when you are going to think about a problem and you have a thought of, you have a line of thought. So you, for instance, look at a specific product and you look at the price and you think like, oh, okay, so I think the price is reasonable. And then you think about the quality. Then you are not forgetting what you just thought what the aspect of price is, right? So you are actually incorporating now the quality, and you are incorporating the price and maybe the product shape and all these things. You're incorporating all together. And that's kind of what we want to reflect when we say sequential. The sequential aspect just comes with time. So we say that this process of decision making takes time, and you are in a one instant of moment of time, you're focusing on a specific aspect, and you are gathering information about this aspect, and then you go to the next aspect, and then you go to the next, and you are so in such a form you're sequentially forming or building your opinion about the product.
Okay, thank you. And you already touched on the application of these computational models in a psychiatric context in order to, for example, help improve people's lives. Could you go a little more into that?
Yeah, so I think what we want to try to understand is these different factors that make people stuck. So what I often, how I often compare it in a more accessible way is that you think about a landscape with like valleys and with mountains, right? And sometimes we feel very much down, and we might be trapped in such a valley. And the question is, how do you get out of the valley? And so there are different aspects, you know. So, for instance, my grandma would tell me when I would be sometimes having periods where I would be of low motivation. My grandmother would sometimes tell me, Nadia, sometimes it's important in life to just go and do. You don't feel motivated, but you will feel motivated after you do it. Don't wait until you feel motivated to do it. So there are these like little wisdoms that we tell each other, right? And sometimes they are taught by our family members, sometimes they are taught by friends or our friends that encourage us, and so on. And one of the aspects that I'm very excited about is that when you are working in a clinical setting, there are actually these wisdoms are proven. They are shown that they can help. And the question is just, you don't always have access to a psychiatrist and work for 3 or 4 years with them to, we call them also build coping strategies, right? So the idea is that you can use these computational models that help you understand how you make decisions, and then the model will tell you the wisdoms. The model will tell you, it's good that you do the way you do, and you can decide whether you want to continue it the way you do. But you could also think of just maybe once do it without feeling motivated. You will see that the motivation comes afterwards. So my vision is really that these models help to understand how you make decisions, to understand blind spots, and to improve well-being by like this self-recognition, right? So it's kind of like helping to understand yourself better, because I think every one of us knows that sometimes we say things that we don't mean, or sometimes we do things that we immediately rue because we notice, oh no, this is actually not what I wanted to do. If I would have known this or that, I would have decided differently, right? And so it's like a navigation system, a way of telling you, hey, look, I observe all the time this specific pattern. If you want, you could now decide to do it once in a different way. And I think that especially when we talk about mental well-being, where our well-being is very fluid, it's fluctuating. I think like probably everyone nowadays feels a bit less secure than they have felt a couple of years ago. Then it's actually good to have coping strategies and to know, okay, how do I cope with different aspects? And the model could help in improving your repertoire of possible strategies.
I have a question, or maybe like I want to summarize what I understood so far and base
Mhm.
my question over that. So when you talked about these models, they don't, or they describe how we make decisions, but don't have like a causal claim. And I mean that in a sense that we don't say, oh, because you looked at this serial last, you picked that one, but maybe it's also you already picked it and then you looked at it and took that. And only if we then look at like individual differences or like group differences, and we see that certain people have certain patterns, we then can investigate like the difference between those patterns. So far, did I understand that correctly?
Yes, I mean, that is a really great point. So I think in science, we are just always very cautious to make causal claims. Because because of two things. So first of all, there can be a unobserved third factor that we don't know, that we have not controlled for, that could like explain the pattern. So it's like the principle with the stork, simply because the stork is more frequent out when babies get to the when babies get born, doesn't mean the stork brings the baby. There is a third. There can be a third underlying factor that would actually that explains the birth rate. And so the aspect here is that we are using these computational models and we don't want to make causal claims, but when we look into a cross species analysis and we use the same models, then we can knock out certain aspects, or we can manipulate or lesion certain circuits, and then you can make causal claims about a specific circuit. But I wouldn't say that in the range of behavior from a human, and also in the environment that we in if we want to model it in real world environment, it's very hard to make causal claims. I think it's actually almost impossible to make causal claims. But over time, you can see patterns, right? You can see patterns, and as you pointed out, and as you mentioned, it's important to capture these individual patterns. And whether they are correlated with certain aspects or not, I don't think this is this is the most clinically important aspect. I think it's important that the person can decide themselves whether they want to, how much they identify to a specific factor. But it's the model that it says, hey, look, you are always looking at that one package, and it looks like this makes you more likely to actually ignore all the others and always choose that. Do you do this deliberately, or do you do it just out of a habit?
Yes, that would be like, or my next question would be, what I think is a consequence of that. The way I understand it is like, and which is also nice, is that it can like help to maybe break certain patterns that we are not aware of or that we maybe even don't want. But I'm thinking like the other aspect of that might also be like people who try to sell you stuff, like the people who place the cereal in the supermarket. And I think like for them it's less powerful of a tool, because then placing like your cereal at the end of the aisle, because then if someone goes through it, that's the last one they see, is like maybe not the smartest choice, because the model doesn't actually tell you that the last one is the best one, but we only like recognized a pattern and can help break that pattern.
Yeah, so actually in marketing or in business settings, they are using the same models to figure out how they can persuade people to choose certain cereals or to make certain choices, right? So I think it's always a question of where you apply these models, and people are free to choose, right? So some people, when you are in a company industry setting, some people choose these models to see how they can enhance the sale of their product relative to other products. In the space where I'm in, we want to use it to improve lives and to improve mental well-being. And so we are going to use these models to increase self-awareness, or to pitch coping strategies to the people, because they might not be aware that there are other possible response options, and so on, right? But it's kind of a powerful tool like AI that can be sometimes misused, sometimes be used without consent from the people, sometimes be very powerful to detect cancer. So I think it's in that space where we need ethics and other research fields that kind of leverage and cooperate with cognitive psychology and with neuroscience and with computational modelers to figure out, okay, what is the ethical, moral way of creating a better world and creating a better setting for everyone.
Okay, I have another question about the computational modeling. This is not my area of expertise, so I'm just always very curious about that. So when you have a question and there are all those different models, how do you decide which is like the best model to apply to a question?
That's a really great question. So there is no real it's a trial and error approach. Sometimes models can simulate or mimic each other, and then it's important to think about, maybe you can have these physiological data like the eye tracking or the heart rate data that can tell you a little bit more about about that stage when people make decisions, right? If you only look at the behavior, you only see the end product of these decisions. You don't have any data while people make decisions. So that can help when you have other measures, other data during the decision-making process. This can help you in refining and selecting specific models. And then it's always very important to simulate a model and look whether it can explain the behavior that you are interested in. So you are comparing the simulated behavior, the predictions that the model makes, and then you look into the empirical data and you say, okay, how closely are they with each other? And then if you would want to say something more about the model than just describing the empirical phenomena, then you would also need to hold some samples back and say, okay, I'm training now this model, and I don't show all the data that I have, but I want that it predicts now a certain behavior of all these data that it has never seen before. So it's like, we call this also generalization, to see like whether a model just explains the behavior that on which it was trained for, or whether it can also make generalized behavior predictions. And so it's an iterative process, and there is no common framework or one universal test that you could rely on. And I think that's the beauty of computational modeling, where I really see it as something different than just a statistical analysis or a regression. Both of them is very important, and they can be used in combination. But it's important that computational modeling is something like an iterative process, and it's an art. And you make an assumption, and then you go and you test your assumption by simulating, and then you compare it to the empirical data, and then you go back and refine your assumption, because the model is never wrong. It's always the assumption that goes into the model that are wrong.
Okay, can I try to phrase an example and you tell me if I understood correctly? So if we go back to the Kellogg's question, so if I wanted to have a model which tells me which Kellogg's are the most bought, I collect some data, I ask some people which Kellogg's they bought, and then I train the model on that and on the behavior of the people. So the eye tracking and maybe some heart rate data, EEG. And then I use like 80% of the data I have. I use it to train the model and tell the model, if people do this, then they're probably more likely to buy this. And if they do this, they're probably more likely to buy this. And then I use the last 20 participants. And if the model is good at classifying which cereal these last 20 participants bought, it's a good model. And if the model has no clue which cereal they bought, it's probably not the right one.
Yeah, or you would want to ask why the 20% cannot be explained, right? Maybe there is something, if you randomly choose the 20%, then the model is missing something. One aspect that I want to highlight as well, and that makes the sequential sampling models, including the diffusion model, so powerful, it's that you would not just collect what serial people choose, but also how fast they choose it, right? So we capture response time and choices. So you could also, for instance, use a reinforcement learning model that has been very often used in different settings and also to train robots and so on. And there it's very common the case that you just use the choices, right? And then you look at how big of a deviation is the predicted choice from the actual choice, and then you have a loop that makes, based on this error, a readjustment. And so we are using these choices, but we also use response times.
Okay, and reinforcement model, could you briefly explain that?
So reinforcement learning models are models that you often use to see how people learn. So, for instance, in the setting of our example in the shopping, we would know, or we would claim that you live at a certain town, you go to the same store, you live there for 6 months. So it's very likely that if you are really into cereals, you will develop a preference towards one specific cereal, right? And so the question is then, how do you learn which cereal to pick during these 6 months? You might once pick one cereal and then have a bad experience with it. Does that mean you never choose it again? Or does it mean that you are just less likely for a period of time, and you are exploring other options? So we call this also exploration versus exploitation trade-offs, and it's important to understand how people form or build preferences or opinions about products, about certain options or choices or behavioral patterns. And in the end, you can bridge them with these diffusion decision models. But the diffusion decision model would then also give you the additional capacity to predict response times. So I would predict not only which cereal you choose, but also how fast you choose it. And based on that speed of choices, I can make more informed claims about what the process is that leads up to that decision.
Okay, and are there any questions where you would say it's very difficult to apply a computational model to?
Yes, I do think that we haven't really bridged or we haven't really explored a lot the possibility of explaining real world data. So we have very often chosen abstract settings where we want to make the real world a bit less complex to account for different factors. And I think this is very important to fine tune the models and to really understand the mechanics. And I think this is important, especially in cognitive psychology, where we have the aspiration to analytically kind of like understand the clockwork, right? It's like understanding a clockwork. But it would be interesting also with the latest push in AI to actually be able to generalize and say we can now we can use these models and use real world data and make stronger claims of what aspects matter in which settings and in real world choices. But so far, this is very difficult.
Yeah, there are a lot of factors in the real world, I think. So
Yeah.
Makes sense.
Talking about real world data and generally you talked about modeling and how models from that were first developed in economics are now used in this context. How do you see the limitations right now in the field? So do you think that computers are really limiting what you can deduce right now, or do you think that in the future new models might help improve something, or is there not even a need right now to have an improvement in the future, but there's so much like to apply these techniques to that the research just hasn't caught up yet with all the possibilities of applying these methods.
That's a really good question. I think it's actually a limitation in multiple aspects. So it's certainly, we know that we could use, we could simulate or estimate more complex model if we would have more computational power. There has been push forward in the space of neural networks that should help us to explore the possible spaces of models in a more systematic way, so that we can be faster in finding the model that fits the behavior best, or in testing different alternatives. But then there is also the aspect where I think must be more crosstalk. So especially in computational psychiatry, clinicians and experts in psychiatry often use theories, but they are implicit informations that they have learned, like these wisdoms, these experiences that they have learned over practicing that within that field and talking to patients for decades. And so the idea is to formalize these theories into the models, and that requires a collaboration and a strong crosstalk across the different research fields. So I think that is one of the aspects where, in order to make these models more powerful, they have to prove their utility in the specific real-world setting. In computational psychiatry, it would be in the clinical setting. In industry or in working with companies, it would be in the marketing setting. In health, public health, it would be in the setting of helping people maintaining their well-being or preventing burnout, like these aspects, right? And that just requires much more crosstalk to formalize theories or hypotheses of what we think, what the factors are that affects people's behavior. So I think that is one of the other limiting factors apart from these models. And of course, there is always the possibility to make these models more complex, to think about what other aspects play a role in groups, but also to think about maybe identifying certain mechanisms in the brain that would explain a specific aspect. And there it's a very hard problem to tackle, because it's always the question, what comes first, right? With epigenetics, it might be that a mechanism that looks dysfunctional in the brain is actually a compensating mechanism, and it would be even worse if you don't have that. But it could also be that it's the one driving factor that makes you feel bad, right? So it's always the question, what is a compensatory mechanism and what is a dysfunctional mechanism? And that really requires more also longitudinal studies. So very often in my field, people have been focusing on understanding behavior at one time shot of a person. We invite them into a lab and we ask them to do a specific task, and then we apply these models and we make statements about mechanisms, which has been working great to figure out fundamental things. But I think over time it will also be interesting to track a specific person and make studies and answer questions that are longitudinally.
I think that's generally something in research that's often lacking, unfortunately.
Yeah.
Longitudinal studies. I don't think it's only in computational studies.
Yeah, I think too.
So when we looked a little bit into what you do, you also work a lot with applying the computational models to ADHD specifically, and also to, for example, success in neurofeedback with ADHD. So could you explain briefly what neurofeedback is and how you apply the computational models to neurofeedback in ADHD?
Yes. So neurofeedback is an alternative treatment that people have been interested in, to see whether we can help children or younger adults with inattention problems by training their brain. And so how this actually works is that there is a specific measure that we call biomarker that we know is sometimes elevated in a subgroup of ADHD. Again, ADHD is very heterogeneous and not everyone has this elevated marker. But one of the markers that is in a subset of people present is called theta-beta ratio. So it's a marker that is based on the frequency of different brain activities. And so the hypothesis of neurofeedback, why we think it works, is that if this marker is elevated and we can make you train to decrease this marker, then you might be able to suffer less from symptoms of inattention. And so people come into this. It's very intensive because people come into the study, and then they come into the lab and they see a rocket, and they have to steer the rocket with neural activity. So they get trained in saying like, okay, just focus very hard and do this and that, and then they can real time see how this is affecting their brain activity. And so the idea is that, like in reinforcement learning, you are reinforcing the good behavior. So you are reinforcing all these aspects that you learn how to do it in order to decrease this marker, and you learn all the other aspects that you shouldn't do to increase the marker any further. And so what we found is that this can be super helpful for ADHD, for kids in particular aged 8 to 12. It can be super helpful if they have externalizing disorder. So what that means is that they have something like a high impulsivity, so that they are also more likely to have conduct disorder conditions aside from ADHD. But it's not really super helpful for those who have also anxiety. So with the computational model, is what we wanted to see is, can we, in the very beginning, before we ask people to train the brain, which takes weeks and weeks, and they have to come in, can we, before they even start, decide or make a prediction of whether someone will likely benefit from it? That can save cost and that can save time. And so what we found is that when they do another task that is totally unrelated to the treatment, we can use these computational models to extract markers that they seem to be deficient in how they make decisions. And depending on the combination of these computational model parameters, we can predict whether someone is more likely to benefit from the treatment or not. So that is one of the aspects that we were able to show in this very large longitudinal study that has been conducted in Europe and in the US, but it has been very exploratory. So what is important with all of these studies is that we, especially in the health or in the clinical field, we want to replicate findings. We want to see whether we can find similar results if we do it in a different study, or whether this was just because of the study cohort or the specific task that we used. So we want to replicate these results. But this is basically the key gist of why we use these computational models. Another aspect is also that very often we have these clinical interventions that we know they can help, because we have seen when we apply it to 100 people that 80% gets better, but we don't know why. And so the computational models can help when we use them together with the interventions to understand why something is working. And when we understand why it's working, we can use it before we even administer any intervention. We can use it to make an informed decision of what is the best option for each person.
I think that sounds really good, because it also helps to make things more efficient and more cost effective. And
exactly, yes, and to tailor to the individual needs.
And also save a lot of people a lot of time, because obviously it's very frustrating when you come in and you think you're going to be helped, and then unfortunately you are one of the 20% for whom it just doesn't work.
Yeah, exactly, yeah.
So we've talked about computational models a lot, and we've also touched on ADHD and psychiatric disorders and the potential applications. What role would you say does cognition play in your research, and how does it tie into that?
So I think cognition is really the basis of, how I see cognitive psychology, or why I got interested in it, is that it's very mechanistically driven. We want to understand how things work. So we are interested in the clockwork, we are interested in the mechanisms. And so everything that is built with these computational models is trying to be very precise and to formalize an aspect that we can measure, right? So it's something that is not only it's not only the specific theories in cognitive psychology that play a role. It's also how we approach the science. And so I think that's at multiple levels cognitive psychology in there. And that is something that I think makes it so powerful, especially in the aspect of psychiatry, because very often we do want to understand why are we in a certain situation? Why do we behave the way? Why does our kid behave the way it does? So the why question is something that is intrinsically driven, a driving, motivating factor for us humans. And that is something that I see very strongly reflected in cognitive psychology.
Yes. And if somebody listened to this episode now, what would you think would be a good thing to take away from this?
I think it's a good thing to take away, to be mindful that these are powerful tools and that it needs crosstalk across different disciplines to make them applicable and useful for the real world. It always needs to be taken with a grain of salt, because all models are wrong. It's just that they are abstracting a specific aspect that seems to be useful to answer a question, so that it requires also to be very precise in the question, and that it's an iterative process. And with the new emerging field of AI, a huge potential to really also use these models to actually make them applicable and useful in the real world.
Okay, then thank you so much for being here and talking to us.
Thank you, Sophie. It was so good to meet you, and also Sönke to meet you.
Yeah, thank you for being here.
You've listened to Science, Conversations on Cognitive Science, hosted by Elisa Palmer, Sönke Löw, and Sophie Kuhn. Produced by Clara Kuhn, Imogen Hüsing, Elisa Palmer, Sönke Löw, and Sophie Kuhn. Produced in collaboration with the Cognitive Science Student Journal. The music was produced by Jan-Luca Schröder. The logo was designed by Annika Richter. Thank you for listening and joining us on our journey through conversations on cognitive science. This podcast is not sponsored and does not give us any financial profit. If you wish to support us, the most effective way is to do so by leaving us an up to 5-star review on your chosen podcast platform and following us on Instagram. You can reach out to us via mail, comment on YouTube, or message us on Instagram. We are always happy to hear your feedback. Thank you again for listening to us and for your interest in science. If you have any questions regarding this episode or any of our other episodes, feel free to reach out. You can reach out to us via Instagram by sending us a direct message at kaleidoscience_pod, or write us an email at kaleidopod@us.de. You can find both links to our Instagram and also the email address in our show notes. We do read all your comments and will also reply to you as soon as we can.